Welcome to The Explainer. Today, we're taking a pretty incredible journey that bridges the gap between the abstract and the physical. We're calling this the blueprint to building. We're going to transition from the mathematical blueprint, those equations that dictate exactly how fast an enzymatic reaction happens, straight into the physical building blocks of the enzyme itself to see how it makes that speed possible. Okay, let's dive right in.
Here's our roadmap for today. First, kinetics and equilibrium. Then, we'll derive the Michaelis-Menten equation. After that, we'll look at the forces driving catalysis and wrap up with specificity and cofactors. Let's knock out the heavy math first so we can really explore the structural world of biochemistry.
All right, Section 1, Kinetics and Equilibrium. Let's set the stage with the foundational rules of all chemical reactions. To really get how enzymes work, we've got to separate two massive concepts in chemistry: thermodynamics and kinetics. On the left, thermodynamics. Think of Gibbs free energy, or delta G. That tells us if a reaction is even possible. It's like the ultimate gatekeeper. But it has a huge blind spot. It doesn't tell us a single thing about speed. And that is exactly where kinetics steps in. Kinetics solves the mystery of how fast. It tells us the actual speed of turning those substrates into products. Now check out how Le Chatelier's principle plays out here. Whether you start with purely reactants or purely products, the system naturally wants to shift. It'll push forward or backward until it hits this perfect point of balance, equilibrium. At that point, you've got a specific ratio of products to reactants, which we write out as the equilibrium constant, or KEQ. But the really important thing here, at equilibrium, there is zero net reaction. The forward speed perfectly matches the reverse speed. And that idea of balance brings us to a super important definition for our math: steady-state conditions. In an enzyme reaction, an enzyme binds to a substrate, forming an enzyme-substrate, or ES complex. In a steady state, the rate this ES complex forms is exactly equal to the rate it breaks down. It might fall apart back into raw materials or push forward to create the final product, but the rates match. Grasping this physical balance? That's the absolute prerequisite for the math we're about to do.
Moving on to Section 2, Deriving Michaelis-Menten. Let's build this famous master equation step by step.
Okay, to make the math actually work, we're going to pull a really neat trick. We freeze time right at the exact second the reaction begins. So, T equals 0. Doing this gives us three massive simplifying assumptions. First, right at the start, practically zero product has formed. No product means we don't have to worry about the reverse reaction messing with our numbers. Second, the substrate vastly outnumbers the enzyme. And third, because of those huge numbers, the total amount of free substrate stays effectively constant early on. These are brilliant little assumptions because they let us simplify what would otherwise be some incredibly messy rates of change.
So what happens when we apply that steady-state assumption to these simplified rates? Well, we can actually isolate the enzyme-substrate complex in our equations, do a little algebra, group our rate constants together, and boom! A brand new constant emerges, the Michaelis constant, or Km. Mathematically, it's just the rate of ES breakdown divided by the rate of ES formation. But conceptually, it acts as the equilibrium constant for this specific enzyme system. It's an absolute game changer for calculating optimized kinetics.
Now, if we take that Km and plug it back into our velocity equation, we reach our final destination, the Michaelis-Menten equation. We also have to introduce a physical limit here. Imagine every single active site on every single enzyme molecule is occupied by a substrate. When that happens, the reaction hits its absolute physical speed limit. We call this maximum velocity, or Vmax. This final equation perfectly ties the whole thing together: starting velocity, maximum velocity, substrate concentration, and our unique constant Km. It's basically the master blueprint.
Let's map this blueprint out visually. As the substrate concentration goes up on the x-axis, look at how the reaction velocity on the y-axis shoots up. But it eventually plateaus as it approaches that physical bottleneck of Vmax. Now look closely at exactly where Km sits on that x-axis. Km isn't just some random number. It represents the exact, specific substrate concentration you need for the enzyme to operate at precisely half of its maximum velocity. It's literally a direct measure of the enzyme's efficiency and affinity for the substrate.
All right, Section 3, Forces Driving Catalysis. Time to shift from the blueprint to the building and see how the physical structure actually pulls off this kinetic perfection.
You know, an enzyme isn't just a static variable on a chalkboard. It's a highly delicate, three-dimensional physical machine working in a totally chaotic microscopic world. So we really have to ask,
What external forces physically influence these optimized kinetics we just calculated? Because if the physical structure is vulnerable, the kinetics are vulnerable too.
It turns out the environment totally dictates the enzyme survival and its catalytic process. First up, pH. Enzymes need really specific pH levels because they're covered in amino acids. If the surrounding acidity changes, the electrical charges on those amino acids change too. Second is temperature, and this is a big one. If it's too cold, the reaction just slows to a crawl. But if it's too hot, you risk thermodenaturation. It's literally like cooking an egg. The enzyme just melts, permanently losing its shape. And third, external chemical forces like ion concentration and water solvation are constantly pushing and pulling at the enzyme structure. Any weird changes in these environmental forces will totally alter or completely destroy the whole catalytic process.
Let's zoom in even further, right down to the atomic level. A globular protein is basically held together by four major forces. You've got ionic interactions between oppositely charged amino acids. You've got hydrogen bonding, creating the internal scaffolding. Then there are those weak temporary van der Waals interactions, keeping tightly packed atoms together. But the most interesting one, the hydrophobic effect. This isn't really about cohesive attraction. It's more about nonpolar amino acids actively hiding from water. This disturbance of water plays a massive role in how an enzyme interacts with its specific substrate.
Scaling those atomic forces up, check out the secondary structures on the left, like beta-pleated sheets. They are held together in a really orderly way by simple repeating hydrogen bonds. But move over to the right, and wow, look at the tertiary structure. This is the incredibly complex 3D folding of the entire chain. It's driven by this chaotic but somehow perfectly orchestrated mix of side-chain interactions, hydrophobic pockets, electrostatic attractions, and these really strong covalent disulfide bridges. This exact, precise 3D fold is what creates the active site environment where the kinetics actually happen.
Which brings us to Section 4, specificity and cofactors. Basically, how do enzymes ensure they're grabbing the correct materials in the first place?
Historically, there have been two ways to look at how an enzyme binds to its substrate. On the left, we have the classic lock-and-key model. It suggests a very static, rigid interaction, right? The key just fits perfectly and securely into the pre-shaped lock. It's easy to understand, but it kind of misses the true geometric magic of catalysis, so look at the right, the induced fit model. This one is dynamic. Think of it more like a firm handshake. As the substrate approaches, driven heavily by that hydrophobic effect and nonpolar interactions we mentioned, the enzyme physically molds itself tightly around the substrate. It completely eliminates empty space to create a custom-fit microenvironment for the chemical reaction.
But here's a fun fact. Sometimes the enzyme's amino acids alone just aren't enough to pull off the required chemistry. And that's exactly where coenzymes and cofactors come in. These are non-catalytic helper molecules, things like organic vitamins or inorganic metals, and they are absolutely essential for the enzyme to function properly. Without them, the enzyme basically lacks the chemical teeth it needs to form or cleave really stubborn chemical bonds.
Let's follow this partnership step by step. Over on the left, we've got an apoenzyme. It's the protein part of the enzyme, sure, but it's totally incomplete and inactive. The active site just isn't ready, so the substrate physically cannot fit or react. But the moment a specific cofactor or coenzyme binds to it, the whole shape changes. It activates, becoming a fully functional holoenzyme. Now, with its chemical teeth locked in place, it's perfectly shaped and totally ready to grab the substrate and execute the catalytic process. As we wrap up this explainer, I really want to leave you with a fascinating puzzle to chew on. Think about this. Classical chemical reactions usually rely on brute force, like extreme heat and high pressure, to make things happen. But enzymes? They operate totally differently. Knowing how highly selective they are and how dynamically they fold around their targets, consider this. An enzymatic reaction is uniquely designed to push and pull electrons in a way that is actually enthalpically disfavored, yet somehow entropilically neutral compared to classical chemistry. So, how does the enzyme's incredible architectural design pay that energetic tax to achieve the perfect kinetic speeds we calculated earlier today? Think about it. Thanks for joining me on The Explainer, and keep questioning the science around you.